But we have a few weird things going on. A hot spot. This is out in the middle of nowhere. Nothing is happening there. There's no subduction. There's no divergence. There's not even a transform plate boundary. Really, we just have a volcano in the middle of a plate, in the middle of the Pacific plate. What is going on? So that's called a mantle plume hotspot. So what's happening is we just have places where some heat needs to be released. Not really sure why these show up, but they do, for our purposes, seem to be kind of random. They're not associated with plate tectonic boundaries. So this is not subduction. This is not a mid-ocean ridge. This is, nothing like that. Hotspots are totally independent of the edges of plates. In fact, Hawaii, again, is in the middle of the Pacific plate. It's nowhere near a boundary, and the boundaries are where we just spent the last quite a long period of time talking about the plate tectonic boundaries. But Hawaii is right in the middle. There's no boundary near this. So what's happening? So we just have some heat being released from probably deep in the mantle. I'm not really sure where, and then that's okay. We're actually finding out more stuff all the time with hotspots because studying Hawaii is really cool. But when hotspots show up on land, that's when they become super dangerous. And those are very important volcanoes to try to predict when they're going to erupt. We'll talk about one that's a little closer to home in a little bit. But first, Hawaii. So I have a little animation to go with this because this is tricky. In lab, you're going to have to show the rate and direction at which the Pacific plate has gone by using Hawaii as an indicator. So for example, we have, we can go all the way to these islands over here. Actually, I don't even think these are above the surface of the sea anymore. These are seamounts. So when we have a volcanic island and is eroded, kind of beaten up by the waves and, landslides and slumps and all that, it's eroded and becomes below the surface of the sea, we call it a seamount. And so a lot of these are seamounts here. Then we have Midway Island, and then we get into the Hawaiian Islands. And the hot spot, the active volcanism, is happening right under the east coast of the Big Island. So this is where like Kilauea is, our active volcanoes that make up the Big Island of Hawaii, Kilauea being the most active. So as we go to the west, we have our other islands like Kilauea, Maui, and so on, and they are no longer active volcanoes. They are being eroded and, in beautiful ways, beautiful mountains there in the ocean, but they don't have any active volcanism. They're old volcanoes and we could date this because this is igneous rock, so fortunately we can radiometrically date this stuff. For example, an island called Niihau is 5.5 million years old. As we go to Midway Island, that formed about 27.5 million years old. Some of these islands are getting closer to 50 and 60 million years old, and so on. So these are the emperor seamounts, and we can use distance between these islands because we could measure that. So the distance between Midway, for instance, and this guy here is, well, if we use a scale bar, don't have one, but let's say it's 100 kilometers, okay? And we have time, whatever 42.4 minus 27.7 million years is. So it's going to give us about 19 or so million years. That's not correct, but whatever it is. We have a time period. So we have a distance and we have time. We do a little bit of math and we can figure out the rate at which, not just the rate at which Hawaii is forming, but the rate at which the whole Pacific plate is moving, which is very cool. We also can figure out direction because the emperor seamounts are pointed much more towards the north. Okay, so I'm going to put an arrow here. Whereas Hawaii, all the way over to Midway and even a little bit further, is more toward the northwest. So what's the order of operations here? What happened? Well, these islands, the emperor seamounts, which are about 80 million years old up here at the top as they subduct below Russia, kind of the Aleutian Trench here from Alaska into parts of eastern Russia. As this is diving down and being subducted up, it's about 80 or so million years old. So these are the oldest ones, and the youngest ones are right here because right now the hotspot is under the Big Island of Hawaii. So the order in which this has occurred was first the Pacific plate was moving north, and then it took a kick about 40 so million years ago, right? Sharp change in direction right about here, and began to move more toward the northwest. Okay, so first was going north, then it began to move more towards the northwest. I hope my video is showing that correctly. If it's not, I'm going to do this instead. I don't know if it's a mirror image or not. Anyway, you can kind of see what's been happening. I don't think it is a mirror image, so it should be showing like that. Anyway, that's how we track the timing and the direction of ancient plate motion. That doesn't tell us what's happening today. We could use GPS for that. But if we want to know what the Hawaiian hotspot, or they kind of stay in the same place, by the way. Hotspots are pretty stationary. They don't really move. The plate is what moves over them. Okay, so this gives us the historic motion of the plate, of the Pacific plate, from about 80 million years ago to today. And that's pretty cool. And the rate has changed. It's sped up, it's slowed down. I think you'll figure some of that stuff out in lab. But what you're probably kind of confused about here from me showing this is how I know that the older volcanoes are here and the younger ones are here. Because if you look at the island chain, maybe I should get a different color pen. And I know this is kind of taking a while, but this is, you know, I don't spend time on stuff. I don't waste your time on stuff that isn't challenging to get and important. And this is both, definitely. So these islands, okay, so we're looking, these are the old islands and this is the young one. Well, didn't they move from here to here? Didn't it go from south to southeast? Okay, that's a big thing that people start to think when they're looking at this. But remember, the hot spot, which is here, doesn't move. Only the plate moves over top of it. So it's like having a pen, all right? It's like having a pen with a piece of paper. My pen isn't moving. This is not a good way to draw on a piece of paper, but it's what I'm going to do. So my pen's not moving, but the paper is, okay? That's what's happening here. So we're actually looking at the opposites of the perceived direction of the islands to determine the direction in which the plate was moving over that hot spot. Okay, that's tricky, but I have an animation that'll, I think, help. Here's our mantle plume, or our hot spot, coming up from somewhere in the mantle. Again, not really sure where or why, but there's a lot of research going on here. And as this heat comes up, it begins to heat up the oceanic crust. So we are going to get volcanism occurring here. So we have volcanoes forming, but that plate isn't just sitting there. If it was, we would have, let me pause this for a second. If it was, we would just have lava piling up over the same volcano over and over and over and over again. We do in other parts of our solar system, in Mars and the moon. We have the same kinds of volcanoes that occur in Hawaii, but they're far bigger. Olympus Mons on Mars is the largest mountain in our solar system. And it's the way it is, where lava has just piled up and piled up and piled up in one spot, because there's no plate tectonics on Mars, and there probably never really has been. So there are mantle plumes, there are hot spots all over the place on Mars as well as the moon in the past. But because there's no plate movement, it just has been just recreating this volcano in the same place, making absolutely immense volcanoes. We don't have that here on Earth, though the Hawaiian volcanoes are the biggest volcanoes on the planet. But because the plate is moving, then we're always forming new volcanoes. We're getting a chain of volcanoes of different ages instead. So this volcano is being moved off, but we still have heat coming up that needs to be released. So we get another volcano forming and another. So we end up getting a whole chain, and they're different ages. The volcano that's over the hotspot right now is the youngest. The ones that have been shoved off longer ago are obviously then the oldest. And we could radiometrically date them, get a really good idea of, you know, how this has happened. All right. Now, what they're not really showing here on this video, some animations do, and feel free to watch any hotspot animation you like, because this is not easy. I know you're watching this, you're hearing me, you're like, oh, duh, well, that's easy. I promise it's not. People have, people really are challenged by this. once you get to an exam, to lab, to the end of chapter questions, to homework assignment, whatever. But what they're not really showing here is that these volcanoes should be getting smaller and smaller because they're becoming eroded. There's no more lava being produced here. Oh, they are showing it a bit. So they're experiencing landslides, which the most of the Hawaiian volcanoes have experienced. Maui, Kauai, huge landslides off of these islands that cause tsunami and could definitely be a problem. But they're getting smaller and smaller and smaller. The biggest islands, like the big island of Hawaii, is the one that is over the hotspot right now and is still growing because Kilauea is active. It's, I think, considered one of the most active volcanoes on the planet. It's erupting a lot, like every few years. Last big eruptions were in 2018, where it grew a bit more. So it builds upwards. But remember, this is how islands form. This is how the Hawaiian Islands formed in the first place. So as the lava makes its way to the edge of that's a good video, I like that. As the lava makes its way to the edge of the island, it builds out the island as well. So all these islands that are in the oceans, whether it's hotspot volcanism like Hawaii, or whether it's a very explosive, deadly subduction zone volcano like Indonesia or Pinatubo or Japan, these islands wouldn't exist if it wasn't for volcanism. So I think that's pretty special, and that's kind of hard for us to remember sometimes because, here in the United States, we don't have a whole lot of, or in the mainland of the United States, we don't have a whole lot of land that is created by, let me go to the next one, by volcanoes. And we think about volcanoes as being very devastating things, and they often are. But in many parts of the world, there are places that wouldn't exist without them. Speaking of volcanoes, a little bit closer to home, the Yellowstone Caldera. Now, I think this is very cool because you may have been thinking, well, okay, if hotspots can just occur randomly and they just occur anywhere, like where heat needs to be released from the mantle, why can't they occur under land? They sure do. And when they do, we get a very different kind of volcanism. In Hawaii, we get these long, fast running, but very low viscosity lava flows, which, are a problem. They destroy homes, they cover roads, they do a lot of things. They don't tend to kill people. And those volcanoes are not really explosive. Well, for reasons we'll get into next week, when hotspots occur under continental rock, you couldn't have a more different situation. They are not continually active like Hawaii. They don't erupt that frequently. But when they do, it's big. It's some of the biggest eruptions on the planet. And Yellowstone is considered a supervolcano. And one of my favorite parts about this is, despite the fact that Yellowstone is the first national park in the United States, I guess anywhere, because I think we invented the national park system. But Yellowstone is the first national park back in the 1800s with Teddy Roosevelt and all that. We didn't know what it was until the 1980s. I'm serious. In my lifetime, we figured out that Yellowstone is a giant volcanic caldera. And what a caldera is essentially a volcano that has blown itself apart. The reason why they couldn't figure that out is because it is so dang big. They couldn't tell. There are other volcanic calderas. There's one in a Crater Lake in Oregon. It's not a crater, it's actually a caldera because it's so large. Craters are smaller. But you could tell it looks like a volcano, and then we're missing the top of it, and it has a nice beautiful lake inside, and good stuff. Yellowstone is so big that they couldn't tell that it had been an ancient volcano until they did some really high-tech aerial photography of it in the 80s. And then geologists studying it were like, oh, that's a volcano that all this cool stuff's happening. And so what's going on in Yellowstone? So we have a huge magma chamber under the continent. So it's embedded in the continental rock, which means you're going to have very, very different behavior than what's happening in Hawaii, because you're melting granite, not basalt like you are in the oceanic crust. Couldn't have a more different situation. And we'll deal with that next week. So you have all this magma, you have a lot of heat. It's heating up the groundwater. So you get geysers, like this picture of Old Faithful here. So you have all these cool hot water features. I don't know if you've had the opportunity to visit Yellowstone, but it's one of the most unique places on Earth. Like there's just not a lot of places like this on the planet that we can go visit, and it's pretty cool. I mean, there's big canyons in a few places in the Southwest United States. There's big mountains and volcanoes in many places over the world, but Yellowstone is special. It's unique. So get there if you haven't. All right, what are we looking at here? All right, so similar. So right now the hotspot is below the northwest corner of Wyoming, and this number is like in millions of years. So the last time this volcano has, well, I guess this caldera formed there about 600,000 years or so ago. It's erupted a few times since then, but that's fine. And then as we go over to the west along the Snake River Plain, which a river flows through in Idaho here, that's the Snake River, and we go over to the west, we're getting into, 15, 16 million years ago. Is the hotspot older than that? I don't know, maybe, but it's kind of disrupted by all the mountains and stuff going on here. So you can't really tell much further than about 15 or 16 million years ago, apparently. I don't know if it's active longer than that or not. But so let's look at this. So right now, this is the volcanic caldera, but the caldera, not these huge mountains, made up of volcano, but these kind of low-lying areas, because each of these volcanoes have been so explosive, they just blown themselves to pieces. So they're low places. They make a valley that a river flows through. Very different than Hawaii, which forms these huge mountains that come up a mile above the surface of the sea, from the sea floor. So we have a very different situation here. We're dealing with a lot more explosive behavior, first of all. And well, that's the big difference, really. So we can kind of follow these, and we make an arrow. Okay, think about it. What direction is the North American plate then moving? If this is the youngest and the oldest are over to the west, what direction is the North American plate moving in? And again, it's easy to think, oh, okay, well, oldest to youngest, so it must be moving to the northeast. Okay, but it's not. Remember, the hot spot has always been here. It doesn't move. The plate, though, has moved. So the plate is moving to, and I think I'm mirror image here. The plate is moving to the southwest. Okay, it is slow. It's not nearly as fast as whatever the Pacific plate's doing, but it is kind of moving to the southwest. The hot spot is staying right there. But as the plate has dragged those old calderas off the hot spot, new ones have been created. So anyway, so that's Yellowstone. And anyway, I hope that was really helpful. Oh yeah, this picture. This is a picture that says 1,000,000 words, and I'm not going to give you another 1,000,000 words. I think I already have. But I love this one because it ties together so many of the things that we're talking about, and again, puts real life examples. This isn't just hypothetical. It isn't like, oh, divergent plate boundaries are where this happens, and convergent plate boundary. Where on our planet do we see these things? What links them together, what makes them similar, and what makes them different from one another. That's kind of cool. And because people don't just study, no one on the planet just studies divergent plate boundaries. They study the Mid-Atlantic Rift, or they study the East Pacific Rise, or they study the East African Rift Valley. They study specific places, and they're all unique. They're all different from one another. No subduction zone volcano is the same. Mount St. Helens behaves differently than Mount Hood, very differently, for reasons we don't always understand yet. So anyway, but this is, I think, a really good example of how we're matching these different places on our planet, making sense of where these plate tectonic boundaries actually occur, and relating them to this real life place. So if you took geology and you didn't realize you would learn a lot about modern stuff happening on our planet and geography, well, I got news for you. And that's, I think, really cool, because I know where so many countries are just because I know where different volcanoes are, right? I know where Gabon is because of a big volcano there. I know where, that this little island off of Italy is called Sicily, and you probably knew that. But, because it has Mount Etna on it, and that's why. So once we start to really branch out and realize all these different awesome places happening on Earth and all these crazy things like an earthquake happening in Nepal, okay, well, why is that? What caused that? Now you probably have a good idea. After a few weeks, when we talk about earthquakes, you'll have a much better idea. So you're making sense of how our world functions, not just throughout its vast history, but today when we hear about something in the news. Okay. So anyway, I think that's really helpful. And oh, okay, cool. Sorry. A few of these different places. A good example of hotspot volcanoes. I have a few pictures here. No. Oh, sorta. Okay. To introduce next week to you, plate tectonic boundaries are going to make us realize that there are different kinds of volcanoes. Okay, so some of the volcanoes are like Hawaii, like right here, where we have our nice low viscosity lava flows, or Icelandic flows, nice low viscosity, lava flows just easily coming up out of the earth. Erta Ale in the Danakil Depression of Ethiopia. Where's Ethiopia? I know, I have an idea because I know about this volcano. Is also a place where we could study broad lava flows happening, and yeah, this guy is right there, sitting right next to it. You can study the lava in this volcano. Pretty cool. You can't do that with Mount Pinatubo, and the reason why is because we have a very different situation occurring at subduction zones. There's a picture of Mount St. Helens, and extremely explosive eruption. This is it's an Alaskan volcano, Mount Redoubt, that exploded 2004, I want to say. And then over here is actually this is an Indonesian volcano. Shoot, I forgot that one. Anyway, but these are volcanoes that occur at subduction zones, whether oceanic and oceanic, like an island arc here, or whether continental. They are creating some of the most devastating volcanic eruptions on the planet. Couldn't be more different than what we see in Hawaii and Iceland and the East African Rift Valley. So why? We kind of got a taste of that today, but we'll get into more of it next week. So different kinds of volcanoes because of plate tectonics. All right. So